Hello, my name is Joseph Shackelford, and this is my lab on magnetic field of a bar magnet. So what is the lab? In this lab, we use an app on our phone as a magnetometer and measure the magnetic field of a bar magnet at different distances and angles. And the purpose is to understand magnetic fields with visual representation and to use the Biot-Savart law to find the magnetic moment of a bar magnet. As for my results, I got mu is equal to 0.01108 ampere meters squared. N was equal to negative 2.5, and I found my magnet to be very weak. As for the principles used, I used the Biot-Savart law, distance dependence of a bar magnet, and linearization of a curve. For the assumptions made, we assume that the bar magnet acts as a magnetic dipole. So finding the magnetometer, so this is the first part of the experiment. So the system is the bar magnet and the surroundings is everything else. The initial conditions that the bar magnet, the magnetic meter on the phone, and a ruler. So the first, we found the location of the magnetometer in the phone by sliding the phone perpendicularly to the ruler and then on axis while checking the maximum Y component and the minimum X component of magnetic field. We then placed a piece of tape at that location. Mine was on the camera of the phone. So taking the data, we took the magnetic field of several locations and distances while attempting to zero out the magnetic field from the Earth in the X direction. We then took that data and graphed it, then linearized it to find out values for N and K. So then we looked to find the off-axis magnetic field of the bar magnet by first finding the distance for where the net magnetic field is 100 microtesla, and then adding that distance to the Y direction as well, giving our distance D. So yeah. So for my data calculations, we used the Biot-Savart law to solve for mu. We found mu to be equal to 0.011085 ampere meters squared. We then used the equation B sub x is equal to k times r to the n. And we natural log both sides, giving us ln bx equals natural log k plus n times natural log r. So from there, that directly correlates to our distance dependence equation, which the slope of our distance dependence equation is equal to negative 3.277, which in our case is equal to n, which is the slope. So then our ln k is equal to negative 19.27. So by putting that to the e, right, we can solve for k, which in our case is equal to 2.217 times 10 to the negative 9. So from there, we can plug that into the Biot-Savart law to solve for mu, and we got mu to be 0.011085. For the coding section, so this is the GlowScript model. Here we model our bar magnet as a cylinder at the origin. We created a function which gives us magnetic field at any point, and we used the input data we found in real axis with mu. We then created 6 points, 2 on axis and 4 perpendicular to the magnet, each 10 centimeters away from the origin, and we found the magnetic field on those points along with the direction of them. We then modeled a point 45 degrees from the origin, which is the distance d perpendicular in the x and y direction, giving it a magnitude of d. The off-axis was found to be 7.063 times 10 to the negative 6 in our simulation. When compared to the actual number, which is 5.19 times 10 to the negative 5, there's an 86% difference between the two numbers, which is pretty large. Some models of discrepancies and sources of error. The magnetometer on the phone may not have been positioned correctly. The measurements may have been off by human error, and there may have been external magnetic fields that may have been interfering with our data. So for the what ifs and whys, what if I hadn't oriented my experiments to compensate for magnetic north and instead laid out at some random angle? How the results have changed. My results may have been less accurate because the Earth's magnetic field may have interfered with the data, leading us to some false conclusions maybe. And what if you were to stick two identical magnets together and to run the experiment again? How would you expect your measurements to differ? The direction would stay the same, but the magnitude would probably increase, maybe double. And as for the conclusions of this experiment, when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. As the magnetometer moves close to the magnet, the measured x component magnetic field increases. The position of the phone matters in terms of ensuring the magnetic field of the Earth does not interfere with our readings of the magnetic field of the bar. The Biot-Savart law can be used to accurately measure bar magnets. And distance is very important when measuring this data. And yeah, that is all. Thank you and have a good one.